All right, today we're going to explore one of the most fundamental and powerful ideas in all of physics. It's the connection between mass and energy, right at the very heart of the atom. And believe it or not, this idea, which explains how stars shine, it all starts with a simple little puzzle about an atom's weight.
So let's just jump right into this, because it's a real head-scratcher. I mean, think about it. If you take something apart, like a Lego castle, and you weigh all the individual bricks, the total weight of those bricks should be exactly the same as the original castle, right? That's just common sense. But when we do this with an atomic nucleus, it doesn't work. The nucleus itself is always lighter than its parts. So where did that missing mass go? To figure this out, let's do a quick refresher on the atom's core. At the center, you've got the nucleus. It's this tiny, incredibly dense ball of particles. And it's made of two things: protons, which have a positive charge, and neutrons, which have no charge. Together, they're just called nucleons, and they make up pretty much all of an atom's mass.
Okay, to really get into this puzzle, we have to get precise. Now, physicists use a special unit for these tiny masses, called the atomic mass unit, or U for short. So a single proton has a mass of about 1.00727 U. A neutron is just a tiny bit heavier, at 1.00866 U. Keep these numbers in mind, because we're going to use them right now.
Let's use a real-world example, the nucleus of an oxygen-16 atom. It's pretty common, and it has 8 protons and 8 neutrons. So if you just add it all up, 8 times the mass of a proton plus 8 times the mass of a neutron, you'd expect the total mass to be 16.12744 atomic mass units. But when scientists actually measure the oxygen nucleus in a lab, they get a different number. It's 15.99053 U. It's lighter. It's measurably, consistently lighter than it should be.
And this difference, well, physicists have a name for it: the mass defect. But here's the really crucial part. This mass isn't just gone. It didn't vanish. It was actually converted into something else. And to understand what that is, we have to bring in one of the most famous ideas in science.
And here is, you knew it was coming, Albert Einstein's incredible equation, E equals mc squared. This is the key. This simple-looking formula unlocks the entire puzzle. It tells us that energy, E, is equal to mass, m, times the speed of light squared.
What this really means is that mass and energy are fundamentally two sides of the same coin. They're interchangeable. You can think of mass as just a super concentrated form of energy. And if the conditions are right, you can convert mass into energy, or you can convert energy into mass.
Now, to really appreciate the power packed into this equation, you have to look at that c squared part. C, the speed of light, is a gigantic number, and when you square it, it becomes absolutely astronomical. This number on the screen, that's 90 trillion joules. That is the amount of energy you would get if you could convert just a single gram of matter, like a paperclip, completely into energy. It is an immense, almost unimaginable amount of power.
So, let's bring this back to our oxygen atom. That missing mass, the mass defect, is what gets converted into a huge amount of energy when all those protons and neutrons come together to form the nucleus. We call this energy the nuclear binding energy. It's literally the glue that holds the nucleus together, fighting against the natural tendency of all those positive protons to push each other apart. And it's also the exact amount of energy you'd have to pump back in to break that nucleus apart again.
And this leads us to the absolute core principle of all of this. The more binding energy a nucleus releases when it forms, the bigger its mass defect will be. So a more stable, more tightly bound nucleus actually has less mass. Why? Because it traded more of its mass for that binding energy. In the world of the atom, less mass means more stability. So how can we tell if a uranium nucleus is more or less stable than, say, an iron nucleus? Well, to make a fair comparison, we use something called the binding energy per nucleon. It's simple, really. You just take the total binding energy of the nucleus and divide it by the number of protons and neutrons inside. The higher that number is, the more stable the nucleus is, on average. And this idea leads us to one of the most important graphs in all of nuclear physics, the binding energy curve. It looks a little complicated, but it's pretty straightforward. Along the bottom, you have the mass number. That's the total count of protons and neutrons. And up the side, you have that binding energy per nucleon we just talked about. This curve is basically a roadmap to nuclear stability.
Let's break down what we're seeing here. On the far left, you have the really light elements, like hydrogen. They have a pretty low binding energy per nucleon.
Then, as you move to the right, the curve goes up, and you hit this peak right around mass number 56. That's iron. These elements in the middle are the most stable, most tightly bound nuclei in the universe. Then as you keep going to the right, toward the really heavy elements like uranium, the curve actually starts to slope back down. They become less stable again. So the big takeaway here is that any process that lets an atom move up this curve towards that stable peak is going to release energy.
And that right there, that gives us two main ways to get energy out of an atom. You can take a really heavy nucleus from the far right of the curve and split it into lighter pieces that are higher up the curve. That's called fission. Or you can take very light nuclei from the far left and smash them together to form a heavier nucleus that is also higher up the curve. And that is fusion.
So let's look at fission first. Picture this. A stray neutron comes along and hits a big, wobbly nucleus, like uranium-235. The nucleus absorbs it, gets super unstable, and then splits apart into two smaller, more stable atoms. When it does this, it releases a ton of energy. But, crucially, it also releases 2 or 3 more neutrons, and those neutrons can then fly off and hit other uranium atoms, setting off a chain reaction.
And why does it release so much energy? About 200 million electron volts per atom, which is a massive amount for a single atomic event. Well, it's because those new, smaller fragments are higher up the binding energy curve. They are more stable. The energy that's released is literally the difference in binding energy between the original uranium atom and its more stable children.
Okay, now let's flip to the other side. Fusion. This is the exact opposite process. Here, you take super light nuclei, like different versions of hydrogen, and you squish them together so hard that they merge into a single, heavier nucleus. Now to do this, you have to overcome the incredible force of those positive protons pushing each other apart, and that takes insane amounts of temperature and pressure, the kind of conditions you'd only find in the core of a star.
Fusion is exactly what's happening in our sun right now. It's the engine that powers all the stars in the universe. Deep in the sun's core, through a few steps, 4 hydrogen nuclei are fused together to create one helium nucleus. And because helium is higher up on the binding energy curve, it's more stable, that process releases energy. And it's been doing that for billions of years. Okay, so let's tie this all together step by step. First, we started with a puzzle. A nucleus weighs less than its individual parts. We call that the mass defect. Second, thanks to E equals mc squared, we figured out that this missing mass isn't missing at all. It's the binding energy that holds the nucleus together. And third, we saw that any reaction, fission or fusion, that creates a new nucleus that's more tightly bound, that's higher up the curve, is going to release some of that stored energy into the world.